Yeah, like I said, my name is Alex, and I'm doing this work alongside the NEST team, who you've heard plenty from. And this will be about how, we can tie in Sunrise, an exciting upcoming heliophysics mission, with lunar interferometer data to enhance its analysis of solar radio bursts. So let's get started. Sunrise is a mission going to launch in mid-2024. Stands for the Sun Radio Interferometer Space Experiment. We're in the heliophysics division, funded through a mission of opportunity, currently in phase C. And it's going to consist of 6 CubeSats in geo-graveyard orbit. Key that we are in space because, as others have mentioned, the Earth's ionosphere blocks out most of the low frequency emission from the sky. So going above that ionosphere is key to unlocking this new window into the universe. And so the primary science of Sunrise is observing these type 2 and type 3 radio bursts, which are associated with coronal mass ejections and different electron jets from flares. And so you can see examples of these radio signatures in single spacecraft data on the left. This is from wind waves, and the features marked B are type 3 radio bursts that descend in frequency quite quickly. And then the A is marking a type 2 radio burst, and it's harmonic, descending a bit more slowly in frequency. But yeah, these descending bands in frequency are the hallmark signature of these solar radio bursts. And we want to connect these solar radio bursts to where the particle acceleration is happening in these space weather events. We know that the radio emission occurs at the site of particle acceleration, and there is some plasma physics going on where the energized particles form a beam, and that beam forms a instability that causes some amount of the energy of the electrons to be converted into radio waves at the frequency of the surrounding plasma frequency. And so for the first objective, we want to understand where these type 2 bursts are coming from within the coronal mass ejection. So just to sketch out a few different scenarios, there's the possibility that it's coming from the shock front, the shock flank, behind the shock at the reconnection in the current sheet, behind the shock, as well as a diffuse acceleration kind of everywhere throughout the CME. And so these are the 4 different scenarios that Sunrise is trying to distinguish between to provide us some basic insights into how this process is happening. The second main objective of Sunrise is to map out the magnetic field line structure by seeing the progression of type 3 radio bursts as they move outwards from the sun, from an active solar region on the solar surface. And in particular, you sometimes have these active regions that give off many type 3 bursts in succession, and tracing each one of them will give us the ability to see the width of how much longitude and how much of the inner heliosphere that single active region can seed with energetic electrons or energetic particles. And so you can see here 2 different scenarios where in the middle panel is a large range of longitudes and areas of the inner heliosphere that are touched by this single source surface. And on the right is a more constrained scenario. So imaging the solar radio bursts in the sky with Sunrise will kind of answer both of these questions for type 2 and type 3 radio bursts. And I touched on this earlier, but key in this observation is that, with an image, we get a 2D plane of sky location of where the radio emission is coming from, but we can actually get the 3rd dimension out using the relationship of the frequency. And the emitting frequency directly tells us what the electron density is of the surrounding heliosphere. And so that's why it goes from higher to lower frequencies, because it is mapping out to the higher electron density near the sun to the lower electron density further away from the sun. And that decreases with some known power law. And we can use past radio data to get this model to convert from solar distance to emitting frequency of a solar radio burst. Just a few words on how the data gets down. So the observatory takes the data. It is observing both radio data as well as GNSS data so that we can, after the fact, determine the locations of the space vehicles to quite a high precision, under 1 meter of absolute knowledge of each satellite. And then the data flows through JPL into University of Michigan, where the Science Operations Center is, where it undergoes some processing to extract the localizations of these radio data by combining the data from each of the space vehicles. And so we've tested this using a simulated coronal mass ejection, simulated orbits of the array, and then pushing these through the processing pipeline to confirm that Sunrise can distinguish between these different acceleration scenarios that you can see in the bottom right, where it provides a visual proof of sufficiency, where you can see the difference between the 4 different acceleration scenarios. Just a word on interferometry. The satellites are separated in about a 1 kilometer to 10 kilometer bubble, and that provides a sufficient resolution to localize the emission to within about 1/3 the CME width. And further, space vehicles that are further apart give us information that is higher resolution, but that's also vice versa, where closer together antenna give us information about larger structures in the sky. And so we can use these simulated orbits along with their projected beam patterns, which you can see on the bottom here. Each spacecraft will have an X and a Y polarization. And so we do have to track the leakage into one and another. So sort of like Nevedito was describing for the Farside array. And the paths that these orbits trace through space also determine the response of the eventual imaging processing that we're doing. So you can see that the longer we integrate, the more distances that we sample with these with our array, the better quality image we'll get out. And so this is a snapshot of that process, where we have a notional 5 spacecraft that gives us some coverage of distances, or UV coverage or baseline coverage. And that corresponds to some dirty beam that we can then use to deconvolve and get a better estimate of what the actual sky brightness pattern is, and then use that to fit the data to a Gaussian. And so that's what we're doing here for each moment in time and each frequency.
1 minute left, sorry.
1 minute left, okay. And so the key here is that with scattering happening in the later parts of these events, Sunrise may not be able to actually image the large structures on the sky due to its lack of short baselines. And this is known to happen after the first 10 or so seconds, after which the polarized signature of a type 3 radio burst disappears and the scattering dominates. And so what we can do is use close together antennas on the lunar surface to enhance our understanding of these type 3 radio bursts and get more information as they evolve and scatter and become larger in the sky. And so on the left here, you see a combined lunar and sunrise image of a type 3 radio burst, just using 2 antennas, which is why you just see the single fringe pattern. And on the right is sunrise alone. And the signal recovered by sunrise is 1,000 times weaker for this highly scattered signal. And so we can go through and do small scale radio interferometers and get much higher quality data on these scattered radio emissions. And so these are just a few different lunar arrays that we've sketched out with prime and the different shapes of those arrays and the response functions that they would afford us to see these more scattered bursts in the sky. And this is all, of course, laying the groundwork for even larger arrays like Farside, which could do the same thing, but at far more sensitive detections, as well as higher quality image reconstructions. And so that's about all I have today. Thank you for listening. Just to recap, Sunrise will be able to do this for the unscattered parts of the radio bursts, but when we combine that with small scale lunar radio interferometers, that will afford us to do more imaging of these bursts as they become more scattered, and also improve any quality of the sky maps that we create. All of this laying the groundwork for future larger lunar arrays like Sunrise, or rather Farside. Yeah, I will pause here for questions, or we can just move into discussion from here. Thank you.